Welcome back. My name is Kevin Doyle. I am the HGSI's Assistant Director of Programs and Operations. We are here today for our second installment of the Spatial Data Science Workshop series. Before we get started, I wanted to thank our partners at Esri and the Harvard Center for Geographic Analysis for making this workshop possible. It's now my pleasure to reintroduce Lauren Bennett, who leads the Spatial Analysis and Software Development team at Esri. Lauren, take it away.
Hi, everybody. I'm Lauren Bennett. I am the lead of our spatial analysis and data science software development team at Esri. I'm joined by my colleagues, Alberto Nieto and Ankita Bakshi, who are colleagues on the spatial statistics team, product engineers who together we all work on all of the tools that we're going to be talking about today. And we're very excited, and we have a lot of content to cover. I think we could talk all day about this topic, so I don't want to waste too much time. I also want to, we're going to talk about tools that are in ArcGIS, but really what we're going to talk about are these methods and how they work and what they're useful for and how to interpret the results. So there's definitely kind of a focus on understanding conceptually how the methods work. Hitting go on the tool is the easy part, right? But understanding what happens when you hit go and if it's even valid to hit go and how to interpret those results, how to communicate them to others are all kind of really foundational. And so that's definitely going to be the focus today. A couple of, I guess, logistics. We're going to have about an hour of content. We'll probably take a couple minutes break. And then we're going to have an open office hours type thing for about an hour afterwards where we'll be answering your questions. If there's lulls in questions, we'll probably just show you some things that we didn't get to show you during the hour. But we're happy to kind of dig in and get into your data, get into specific questions about workflows. We don't have the capability to do breakout rooms in this Zoom meeting, but we can, if a particular question looks like a good one to kind of take offline and dig in deeper with one of the other folks on our team, because we've got quite a few folks from our team also joining to help in that office hour session, we can easily do something like send you an invite for a separate Zoom or a Teams meeting. So we'll definitely do some of that as well during that hour. The other piece of logistics I want to mention is that Kevin sent around links to the projects that all of our demonstrations will be using today. And that is, so you can open that up and follow along with these demos that Ankita and Alberto will be showing. But you definitely don't have to. So if it's useful to you or you're familiar enough with the software that you want to kind of click along and follow along, get to know the data as we do it, please feel free to do that. But also you will not lose anything if you just watch and maybe try to dig in deeper after the session. So really up to you, but those resources are there for you if you want to get your hands dirty. Okay, so we are going to get started. So we want to talk a little bit about kind of what is clustering and how do we think about it in the context of spatial data. And we kind of think about this in the context of two different approaches to clustering of spatial data. So there's statistical clustering and there's these machine learning based approaches to clustering. Now, last week we talked about clustering using statistics, and we talked about the kinds of questions that we can answer when we use statistics for doing this kind of spatial clustering. And really oftentimes what we're doing is we're trying to figure out if the spatial pattern that we're seeing could be one instance of a completely spatial random pattern, right? So if we picked up a bunch of data and threw it on the map, how likely is it that this pattern that we're seeing is just that kind of a random pattern? Because clustering does happen randomly, and we really want to be confident that the clustering that we're seeing is significant enough, meaningful enough to be clusters that we really care about. Because if we just throw our resources into random clusters, we're not likely to get a big return on that investment. And so we talked about how we can use p-values and z-scores and this null hypothesis of complete spatial randomness to answer that question and find these clusters of high values and clusters of low values. We also talked about outliers. And I know that that session was recorded and will be made available. We also have a lot of resources that we'll point you to at the end where you can dig in a lot deeper to statistical clustering if that sounds interesting and you're bummed you missed it. Today, though, we're going to focus on clustering using machine learning techniques. So this is a kind of unsupervised type of machine learning where you don't give these algorithms training data, but rather you really let the algorithms figure out where the natural clusters are in your data. And that can be based on purely location, just the spatial locations of your data. It can be based purely on the values in your data, the attribute values or the fields in your data set. It can be based on locations and values, certainly adds a little complexity to our clustering, but we've got tools to do that. And then also locations, values, and time. So lots of options for how we can use machine learning techniques to kind of find those natural clusters in our data. And we often get questions kind of, so what should I use? You've got all these different clustering methods. What should I use? Should I go statistical? Should I go machine learning? I'm sure it's not a surprise to you that people these days really want to lean towards machine learning under all and any circumstances, it seems, because it's definitely the kind of cool thing to do. And machine learning algorithms are incredibly powerful. I mean, we have a whole session on them. We're going to talk about them. I love them. But I don't love them over a focus on the question, right? I mean, nobody's problem is that they need to use machine learning. People have a problem they want to solve, a question that they want to ask. And I think the really important thing is to just really think about what your question is. Sometimes the most appropriate method is going to be a machine learning technique. Sometimes it might be a more traditional or a spatial statistics technique. Sometimes it's going to be some wildly simple descriptive statistic that's the answer to your question. And really focusing on that, I think, is something that's really important. And perhaps in our swing of the pendulum towards really caring a lot about analysis, which is very exciting. I feel like the whole world understands how important analysis is now more than ever. Maybe we've gotten a little swept up in the newest method, the buzziest approach, and really focusing on the problem is incredibly important. Okay, so we're going to start by talking about actually kind of a set of methods that are all accomplishing this goal of finding density-based clusters. And these methods are all about the locations of features. So really what you have is a bunch of points on a map. And you're trying to kind of get the algorithm to find these natural clusters in your data. And the way that I think about this is it's kind of like we already can see the clusters. Before I turned them on, if I had asked you to circle the clusters on this slide, we all could have done that, right? Now, we might not have all circled the exact same things because sometimes our idea of what a cluster is may differ, but we generally have an idea of what the clusters that we're looking for look like. And what we're trying to do is try to tweak the algorithm, try to tweak the parameters of the algorithm so that it finds what we're looking for, so that we can kind of automate the process of finding those clusters. Because most of the time, the data that we're trying to find clusters in isn't 25 points on a map. We're talking about hundreds of thousands, millions, billions of points, and we're trying to automate that process because it's time consuming and we have limited resources. So we have a number of different methods that we can use to do this kind of density-based clustering, and they have pros and cons. They kind of each have they each have questions that you might be asking that are more appropriate for that particular method, and we're going to walk through each of them and kind of conceptually how they work.
So as Lauren was talking about, there are three methods that density-based clustering uses, and she started talking about DB scan with a defined distance and a minimum amount of features per cluster. So she had elaborated that there's an example here with 5 features per cluster. And the tool will identify something called the core distance, which is the distance that it takes for any given feature to reach that amount of features around it. And it will compare that to what you have passed to the tool as your search distance. If it finds that amount of features, if the core distance is lower than the search distance, essentially, then that feature becomes part of a cluster. Alternatively, if your core distance, again, the distance it takes to find that minimum amount of features in that cluster is greater than your search distance, then the feature that you're analyzing, that the tool is analyzing at that point, is considered noise. And that method is, I like to think of it as a very great method when you have very specific parameters that you know you have to meet for the definition of a cluster. If you know that you're looking for retail presence and you need to have a certain amount of stores in a cluster before you pay attention, and you know that all that retail has to be condensed to a particular region, maybe a block, a city block, then you can pass those as the parameters for the search distance and the minimum features per cluster. And the tool can be really well explained because it's very manual and you're telling the tool exactly what it means to be a cluster. Alternatively, there is a method called HDBScan. And this method is almost purely data driven. It will adjust the search distance based on the density of the input points that you're passing to the tool. So in this case, in HDBScan, you tell the tool the minimum features per cluster, but you do not tell it the search distance. It will calibrate that for you, evaluating the entire study area and the different densities throughout your input points. So this case, this type of method, I think, is really useful as a starting point often when you don't know what the definition of a cluster might be for your problem, but you're trying to evaluate what the tool might find in the data for you. It can also be useful in cases where your study area is quite large and you have both dense urban regions and really sparse suburban regions, and you want the single tool pass to redefine what it means to be a cluster in both contexts, right? And find both types of clusters. And then there's the third method type, which is called optics. And optics is perhaps the method that gives you the most tuning parameters to really define what it means to be a cluster and really interpret what it means to be a cluster. So with optics, what the tool will do is it will reach out feature by feature and calculate all of the distances and create what we call a reachability distance chart. So in this reachability distance chart, on the x-axis, you have all the features in order, in rank order. And on the y-axis, you have that distance plotted. And if you think about this chart, those peaks in that reachability distance chart could be really distinguishing points between a cluster and another cluster, or a cluster and a noise point. So in this case, you might see those peaks really start to distinguish the study area into these three clusters. However, if you think about it almost like a water level, if you lower the water level, you might start to point out different clusters. For instance, if this area, if this distance between this point and that point reaches out beyond that water level, then you might actually be able to find additional clusters of additional detail in your study area. And that's governed by a parameter called cluster sensitivity that we'll get into in the demonstration. So with optics, I think it's really useful to use when one, you're trying to adjust for different densities in your study area, but you're also really trying to explain how the tool found these clusters, because the reachability distance chart is really useful to see and interrogate the results and defend them. So in summary, there's three methods. DBScan, very manual, it's very fast because it doesn't have to do the search for the parameter values. You're telling the tool what it means to be a cluster. HDBScan, which is data driven, requires the least user input. You just tell it how many features per cluster you need, and it will do the rest of the work for you. And it's very useful as a truly exploratory technique when you don't know a lot of the parameters for your clusters. And then optics, which is very, very flexible for fine tuning of what it means to be a cluster and includes that reachability chart that can help you explain and defend your results. It can be computationally intensive in some cases when you let the tool determine some of those parameters for you. So from that, I want to share a quick demonstration of density-based clustering. So for this demonstration, we're going to put on the hat of a business analyst at a large bank, and this bank wants to create branches throughout the country. But for the demonstration, we're going to focus on a single city, Raleigh, North Carolina. And a useful technique for retail site selection is to look at existing clusters of retail. In this case, we're going to look at restaurants in the city of Raleigh and Wake County. And visually, you might already see some clusters. You might be able to circle some areas that may be interesting if you're trying to prospect for a site. However, we want to find a method that you can both explain and repeat, not just for this city, but for every other city that the bank wants to expand to. So we're going to open up density-based clustering, which is a tool that you can find in Spatial Statistics toolbox. And very simply, we're going to fill in the parameters, passing the input restaurants, selecting our clustering method, in this case optics, and then designating the amount of features per cluster or the amount of restaurants per cluster, and let the tool run. So in this case, I selected optics because there are both dense urban regions, so the city of Raleigh with a lot of people that maybe walk around and shop and dine, but also some suburban regions where people are more inclined to drive, and we want the single tool run to find both types of clusters. So optics is well tuned for that. Plus, we get that reachability chart in the output that we can use to interpret the results. So right off the bat, we can see these peaks and valleys start to distinguish the restaurants into clusters and noise, right? And we can see that most of the city of Raleigh, at least the downtown area, becomes a single cluster, and that's distinguished from other suburban areas and other towns in the county. This may not be the most helpful, at least at start, for citing a branch for a bank yet. And if we zoom into that area downtown and make that selection, you can almost see that there could be additional clusters here. So let me make that selection. Sorry, let me select that again. You can see that there's a peak here that could emerge. If I select all of the features here on the right side of the chart, there could be a cluster there. If I select the features here on the left side of the chart, there's likely a second cluster there. And once again, if you lower that water level that defines the peaks from the valleys, we could find additional detail that gets at that problem question that we're thinking about, which is finding intersections and shopping centers for a potential branch for a bank. And the way we govern that water level is by using this cluster sensitivity parameter. Now, the tool found one for us. It's a value between 0 and 100. And for our tool run, to see what value it used automatically, we open the messages window. It tells us that the cluster sensitivity was 25. The second best cluster sensitivity is 90. So we're going to use that second best cluster sensitivity. And since we're now starting to tune the runs of the tool, I'm going to be a bit more specific with my naming convention. So I'm going to say 5 minimum features per cluster, 90 cluster sensitivity, and let the tool run. And let's close the results of the previous run and have a look at the results. So right away, we see a lot more detail in these clusters. It's getting closer to that type of answer that the bank would be looking for, specific intersections or even shopping centers, right? Let's open up the reachability charts. That region in downtown Raleigh is now split up into distinct clusters that could be a lot more useful. Let's zoom into those peaks and valleys. So that valley or that peak now defines multiple clusters on one side and the other. And even within the other valley, you start to see other peaks emerge. So you see this very dense area, this very dense neighborhood in downtown Raleigh, distinguished from another neighborhood in downtown Raleigh that could be very useful to analyze further, right? Another thing that you get with this result is the features per cluster chart, because at this point, once you've identified these dense areas of retail, the next question the bank would likely ask is, what are the clusters that have the most restaurants? So with this chart, we can do that. I'm going to select the noise points. We don't care about those at this point, so I'm going to switch the selection and make a layer from that selection. So we're now just focusing on our clusters. And let's take a look at that chart of just the amount of restaurants per cluster, ignoring noise. So now we have these really promising clusters. So there's the top cluster with the most restaurants. Downtown Raleigh, the one that we were looking at just a few moments ago. The second cluster is actually the second area that we were looking at a few moments ago. Those are promising downtown areas, but perhaps a bit obvious. The third one is maybe a bit more interesting. So if we zoom into those areas, this is a shopping center in the suburbs, and this is just the type of retail area that a bank would be looking for that type of branch to satisfy a lot of the demand in that area of the city. So this becomes a promising location to study, right? And yet again, another question starts to come up by the bank. They might ask, what is the type of retail that's there? How recently was it built? Is it new enough so that we could beat our competition to that type of area? So in order to incorporate time, there is a time field parameter in the tool. So we're going to look not just at location, but also time. And we'll tell the tool to analyze the opening date of the restaurant, telling the tool that you have 2 years to search for your cluster. We're going to increase the criteria for being a cluster to 15 restaurants within 2 years. And we'll also specify a distance, in this case, 3,000 feet. And again, a best practice I recommend is to be very specific with your naming convention so that you can remember which layer corresponds to what. So we're going to say 15 restaurants per cluster, 3,000 feet within 2 years at 90 cluster sensitivity. Let's run that. And let's zoom back out. All right, let's have a look at the results. So very interesting, we get very specific clusters, right? This is getting to these really specific answers that might be very interesting for the bank. And you get this new chart, time span per cluster, that gives you additional information about the cluster. When were these restaurants opened in this case? So let's have a look at that area that seemed promising, that shopping center. If we select those restaurants, we actually find out that they started being formed about 20 years ago now. And perhaps there's already an established bank presence there that we don't want to tackle. So maybe there's other promising clusters that we may want to target at this point. Namely, there's this one cluster over here with really dense temporal clustering, right? So these restaurants came about in a really close time space, actually just within the past year. And they happen to be another shopping center called Wilder's Grove. And it also happens to be a commute pattern. So basically people from the suburbs commute into the city and back out. And these types of areas are really important to a bank looking to site a new branch, because they not only are they good for the branch itself, but also for marketing as people drive back and forth from the city. So that's a few examples of using density-based clustering. We used optics, but there's certainly other ways to use the methods for other types of questions. And I'm going to hand it back to you, Lauren, if your computer is back up.
I love that demo. I know that I think that it's just a really good example. I think it's a really good example of a couple things. One is the idea that even something simple like just finding clusters of points in the landscape can give us so much information. Like even if you weren't at a bank, like even if you just wanted to kind of understand a new place based on the neighborhoods in that place, using density-based clustering to find those little neighborhoods is really valuable. We were also talking yesterday while we were preparing for today about how interesting it would be to explore if we could use density-based clustering and time, much in the way that Alberto just did to find that area with newly built restaurants clustered together, to perhaps explore gentrification. Maybe kind of an early warning sign for gentrification would be a bunch of new buildings going into a particular neighborhoods, or a bunch of new restaurants going into a particular neighborhood could be kind of an interesting way to detect gentrification, as just like another example. So I think there's a lot of examples of how that kind of clustering can be very valuable as part of bigger workflows, right? It's rarely that the clusters are going to be the be all end all of some big complex problem you're trying to solve, but rather they're either very useful exploratory tool for getting to know your data, for developing hypotheses, or those clusters become, categorical variables in a model. They become study areas to do further research. So lots of kind of opportunities for how you can use those clusters. kind of downstream in a workflow. And I think that's true for really all the many of the clustering tools, is that the goal isn't just, okay, I'm going to make these clusters and that's the end of it, that it's usually part of a bigger workflow. Although I'd say probably most analysis methods, that's true, because most problems are solved by breaking up that problem into really truly solvable problems and putting them together, because most problems are pretty complex that we're trying to solve. Okay, so next we want to get into multivariate clustering. And we're really going to explore two approaches to multivariate clustering, one that does not incorporate space and one that does. Because what we've found and what we know is that even methods that are not inherently spatial, and we do a lot of work on inherently spatial methods where the location of features is actually kind of included in the mathematics, included in the algorithm, whether that's spatial relationships, proximity. But there are definitely lots of traditional methods that don't include space that can still be really valuable for spatial data, for solving spatial problems. And very often, even non-spatial methods can be valuable for us understanding spatial patterns. And I think we'll see a little bit about that through the slides. Okay, so we want to talk about multivariate clustering. And the goal when we're doing multivariate clustering is to create groups that are as distinct as possible, so that we want them to be very similar within the group and very dissimilar between groups. So we want the groups to be as different as possible from each other, and as all the features within the group to be as alike as possible. And so that's our goal when we're doing multivariate clustering. So we want that dissimilarity between, and we want the similarity within. Now, one of the most popular ways to do this kind of multivariate clustering is using Kmeans. And the multivariate clustering tool in ArcGIS is really just a implementation of Kmeans++ inside of ArcGIS. And our goal in a lot of these methods, like density-based clustering exists in all sorts of software packages, so does Kmeans. And kind of what we think about when we put them into the software is, how can we make these as useful as possible for spatial data? How can we provide defaults that are meaningful? How can we provide outputs, like for optics? We saw the reachability plot. We saw the number of features per cluster. We saw that time span when we incorporate time. It's like all these things that make interpreting the results as easy as possible and thinking spatially about them as easy as possible. So what we're doing when we do this kind of K-means analysis is we have a series of variables that we're interested in. In this case, we're looking at population density, average income, and median age. And every feature in our data set has all of those variables. And you can kind of think about it as plotting all of that data in data space. In this case, we're looking at kind of three-dimensional data space. It's impossible to illustrate, but you can imagine that this can go into a very multi-dimensional data space, right? You're not limited to three, but we are limited in our ability to illustrate more than three. So you get the idea. And so really, I mean, in a lot of ways, you can think about it like what we just did with density-based clustering, where it's looking for these natural clusters in space, but now instead of space, it's data space. And we're looking for that natural clustering in data space of all three or however many attributes you're including. And so we find these kinds of natural clusters, and depending on how many clusters you want to find, it will break it up in different ways. And we do have approaches that allow you to figure out at what number of clusters, the K in K-means is the number of clusters you're trying to create. And so we do have a pseudo F statistic that's part of the method, which if you don't choose a number of clusters, it will try to figure out what's the number of clusters that is going to ensure the most meaningful clusters that do the best job of kind of maximizing how similar they are inside of the cluster and how different they are between the clusters. Now, another really important part of the output, in addition to just a map that tells you what cluster each feature belongs to, is this set of parallel box plots that we create. Now, if I gave you a map and I said, I have done this incredibly sophisticated analysis, you have a red group, a green group, and a blue group. Congratulations. You wouldn't know what the red group means. You wouldn't know what the blue group means. And in order to understand those groups, you really need to be able to evaluate how each variable played a role in creating that group. What are the unique characteristics of each group based on the variables that were used to create them? And so the parallel box plot gives us a sense of that. So for instance, we can see that, so in gray is the entire data set, the averages for the entire data set, the distribution of the entire data set. And so we see how each group falls relative to that whole distribution of the whole data set. So we can see, for instance, that the red group here is the group that's kind of high along all three. It's got high population density, high income, high age. This outlier orange group or yellow group is a bit different, right? We can see it's kind of an outlier where it's got low population density, high income, and kind of average age. It's different than pretty much everything else. Or, you know, the purple group being low on all three. And so we can really start to interpret the output based on that parallel box plot. I will also say that Kmeans, while it's not a spatial method, does output a map. And one of the things that we know, there's something called the first law of geography, and that is that everything is related to everything else, but near things are more related than distant things. So it's saying that things that are closer together are more related than things that are farther apart. So even though Kmeans isn't a spatial method, we do expect that things that are close together often are going to have similar attribute values, right? And so we often see spatial patterns in the output map, even though the method itself is not spatial, and that can give us a ton of information. And what's cool is that sometimes we'll see that there's a cluster of the red group that's in, you know, one part of the country and a cluster of the red group that's in another part of the country, because they don't have to be near each other, but they have similar characteristics. And so we can learn a lot about the spatial patterns in our data, even from a method that's not spatial. But we also have a method that is spatial. So the spatially constrained multivariate clustering tool is based off of an algorithm that's called Skater. And it similarly is going to use attribute values to cluster features, but it also has proximity constraints. So the way that the method works is it builds a minimum spanning tree. The only way that you can be connected in that spanning tree, in that minimum spanning tree, is to meet the spatial proximity constraints. And then the length of those lines represents their distance in data space. And what we do is we go through cutting those longest lines to create clusters. And what we end up with is, again, a map with those clusters. We have parallel box plots to help us understand them. I will say that the spatially constrained clusters that we create are virtually never going to be as optimal from a variable perspective as Kmeans, because we're constraining them spatially, right? We're forcing them together because of space. And so it's really a kind of an optimization problem, and we're kind of compromising on how similar they'll be within the group when we add that constraint. But nonetheless, sometimes the clusters that we're looking for need to be contiguous, and so it can be a really valuable tool for that. And Ankita is going to show us spatially constrained multivariate clustering in action.
Okay, thank you, Lauren. I'm going to share my screen now. Can you see my screen? Perfect.
Yes.
So in this demo, we'll be looking at an example of house pricing in King County, Washington. So each point on this map represents a house, and that house has associated attributes to it, like price, number of bedrooms, the area that the house is taking. So all those attributes are associated with all these points on the map. But before we get started with the analysis, I just want to pose a question, like, has it ever happened to you that you wanted to live in a place which is closer to your university or closer to the place you work, but that's mostly the place which is the most expensive part of the town as well. And as you move farther away, the prices are relatively lower. Well, it turns out it's not bad luck, but housing is a very spatial problem, like the way we have all experienced it at some point in our lives. So if I were to model this problem, if I were to model what affects housing prices in this entire county, that would be very difficult because there are so many spatial factors that are at play. So even in this example, if I just symbolize my data set by house prices, we kind of start seeing those spatial factors, like the prices that are near the lake are, the houses that are near the lake are more expensive than the houses that are more inland. So what I want to do is want to split this area into different regions based on some attributes, such that the region itself are homogeneous. So like the way Lauren mentioned, like this spatially constrained multivariate clustering, what it would do is it would create these clusters so that the clusters are homogeneous and they're as distinct from each other as possible. So then we can take those regions and fit our linear regression models to understand housing behaviors in those regions. So to do that, I'm going to use spatially constrained multivariate clustering tool, which we can find in the mapping cluster toolbox. I'm going to open this tool. And my input feature is the King County housing pricing data. And for my analysis variables, I'm going to use price and square foot living. And I'm going to create regions based off of these two analysis fields. And I also want to provide an output table to later evaluate my clustering results. I'm going to run this tool. One of the parameters that I want to talk about in this tool, which is number of clusters, what you can do is if you know exactly how many number of clusters you're looking for in your data, you can provide that number here. So let's say you have 5 administrative zones, so you want exactly 5 number of clusters for the data that you're analyzing. So you can provide that number here. But sometimes you don't know that number. Like in this example, we haven't provided that number at all. So what the tool will do, it will find that optimal number of clusters for you. And in this case, the tool found 2 clusters. So one in the green color, in the blue color, and the one in the red color. So we kind of start seeing some things that we were already seeing by visualizing the pricing data on the map. But to really understand why the tool found these 2 clusters, I'm going to look at this pseudo F statistic chart. So what pseudo F statistic is, it is a ratio between the variance within the cluster to the variance between the clusters. So in other words, higher the value of pseudo F statistic is, more homogeneous the group is and more distinct it is from the other regions. So by looking at this chart, I can see that for number of clusters 2, the tool found out the pseudo F statistics is highest, and that's why we got the result 2. And as the number of clusters increased, like from 3 till 8, it decreased a little bit, but then after it just dramatically reduced, like the pseudo F statistic just dramatically reduced to a very low number. So what we can see from this elbow is that even if we increase the number of clusters, we are compromising on that homogeneity, but not a lot. So if we do want to find finer clusters, so if these 2 clusters, this red cluster is such a big cluster that is covering almost the entire county, but we're not able to kind of tell a lot of things about what goes spatially into these smaller areas. So I do want to run this tool again with 8 number of clusters to find those finer results. So in this case, I'm going to run the tool with 8 number of clusters. And the tool is writing the results. So unlike Alberto, I didn't provide a good name, which I always forget. And all of the names of my output features are test 1, test 2, test 3. So I would definitely recommend you giving a better output feature name and learn from Alberto and be better next time. I'll be better next time. But in this case, now we found 8 clusters. So now we can see that those big red clusters and the blue clusters are now split into smaller clusters, so we can get finer results and finer clusters. And to really understand this, we are going to use charts. And as Lauren mentioned before, the box plot really helps you understand like the result of your analysis. So I'm going to zoom into this box plot and start analyzing my clusters. So the color on the chart matches the color on the map of the cluster. On in the blue cluster, we can see that it has the highest price, and the blue, green, yellow, and all these clusters are above the 3rd quintile for price and also for square foot living. So the blue cluster really corresponds to a cluster where price is high as compared to the green and the yellow cluster. But the living space is actually smaller. And on this map, if I select this cluster, I can see this is the area east of Lake Washington. And this is probably the most desirable part of the town. And maybe the living space is not the driving factor of home prices in this region. Similarly, this green region is located on the island of Lake Washington, which corresponds to houses with larger living spaces than the blue cluster, but it's still very high. The prices are still very high. And if we go down to these clusters in pink and red, we can start seeing that these, the areas in pink are a little cheaper than the areas in red, but then you can get a house with almost the same size in cluster pink for a lower price than the cluster in red. So these different compositions of the clusters help us explain why a single regression model couldn't have worked alone if we wanted to see the behavior and the factors that are driving house prices in the entire county. So really need to find these finer clusters to understand these behaviors. And with that, I'm going to hand it back to Lauren to talk about the last clustering technique.
So I think that one of the things that, well, so another thing that we could use the output of that clustering analysis for, certainly we can break it up and use each of those as a separate study area for regression analysis. There's also lots of examples of using those kinds of clusters. You know, it's not uncommon in, you know, we might do a random forest model, and if I'll ask someone, okay, did you think about space? They'll say, oh yeah, I included zip code as one of my attributes. And certainly that's something, but it's not a very meaningful way of incorporating geography, right? It doesn't acknowledge, you know, that all it's saying is these all share a zip code. There's no concept that this zip code's right next to this zip code and that we're related by being in proximity. And so creating regions like this or clusters like this might be an alternative way of incorporating geography in a way where those clusters, instead of a zip code, you're using a cluster that at least you know has similar characteristics and maybe is more meaningful than just random zip codes. One of the things I also really like about that I think really strikes me about both the demo and density-based clustering and how we're talking about multivariate clustering is, while machine learning is often thought of this kind of black box, there's still an iterative analysis process, right? It's not just like push the button and go and you get your answer, which I think is what a lot of people expect using machine learning to be like. But actually, there's a lot of work on the part of the data scientist, on the part of the analyst, to be kind of a subject matter expert on the problem that you're trying to solve and really understanding what your question is so that you can tune those parameters to most accurately reflect the question that you're asking. Because I mean, I know it's called machine learning and it's artificial intelligence, but it doesn't actually know what question we're asking. We have to inform it with those parameters. And often that can be kind of an iterative process to tune it, to get it to kind of match up with what we're looking for. Okay, so the last one that we're going to talk about is build balanced zones. So this, in a lot of ways, is kind of asking an opposite question to what we've been doing with multivariate clustering. So with multivariate clustering, we're trying to create these groups that are similar within, but different between. With build balanced zones, we're actually trying to create groups that are each alike. We're trying to create groups that are kind of uniform in their characteristics. So we would really want, you know, the box plot of the groups we create with build balanced zones to have them all kind of fall in the same exact place because they'd all be reflective, they'd all match essentially. And so it's a very different question. And the way that we accomplish this is using a genetic algorithm, which is pretty cool. And we're going to talk kind of conceptually about how it works. Now, the first thing that we have to do when we're doing this kind of zone building is figure out how we want to kind of constrain the zones. Do we want to say we want to create zones that all have about 100,000 people in them? And however many zones you need to make to get to that 100,000 people is great. Do you want to say, I need to create 10 zones and they are, and that's all I care about? Or is it, I want to create 10 zones, but I want to be balancing out a particular attribute as you do it? And so there's these different kinds of ways that we specify what kind of zones we're trying to create. We can also further constrain our groups to, or select groups based on their ability to optimize to have as equal areas as possible, to be as compact as possible, to have the same number of features, if that's something that we care about. Or we can incorporate additional attributes that we want it to try to balance. And it will use that to, if it's choosing between 10 different potential outputs, it will use these selection criteria to say, oh, well, this one does that the best, and so we'll pick this one. And really, this is very much a spatial optimization problem. And so the reason that we use a genetic algorithm is because there are countless combinations of these different criteria and selection criteria that we, and spatial layouts that we want to consider, and we just can't consider them all. And so really, it's this way of heuristically figuring out and getting as close as we can to an optimal solution. And so what the genetic algorithm does is it starts with a random seed, and it uses that to create zones that meet the criteria that we've set forth. And each of those zones and that solution receives a fitness score. And it does that over and over again for a number of different potential solutions, and it scores them based on that fitness score. And so each of them will have a fitness score, and the lower the fitness score, the better. And what we do is we then take the top 50% of fitness scores, meaning the lowest ones, and they move on to the next generation. So you can really think of this, it's called a genetic algorithm, and they borrow from all sorts of kind of cool genetics and evolutionary concepts, but you can think of this really as survival of the fittest. So the fittest 50% move on to the next generation, and they essentially procreate, cross over, create new offspring, and we have another generation. That generation gets fitness scores, lots of things move around. There's a lot of kind of optimization happening here to figure out, to create as much difference as we can in this next generation. Those fitness scores get calculated and the next 50% move on. And that happens over and over again. There's also lots of other kinds of concepts that come in, things like mutations, and even aliens can be introduced into this to figure out, to get to kind of that optimal solution. And at the end of the day, what we're looking for is over the generations, we expect the fitness scores to go down and down with each of those generations. And very similar to what we saw with the F statistic, we're looking for the points at which we're no longer getting a benefit from going to more generations. We're finding that point where, well, we've reached kind of the optimal fitness score. And so one of the solutions within this generation is going to be the best one. And we use that to choose. And this is definitely one of those ones that I think really works best when you see it in action. So for our last demo, I'm going to pass it back to Ankita, who is going to show us build balance zones in action.
Okay, so before we get into the action, like the fun part of doing the analysis, I do want to quickly talk about one thing that we generally do when we have a data set. We do want to understand what this data set contains, what field it has before doing any analysis. So right now on the map, what I have is these are the affordable housing pipeline projects in San Francisco. So these projects help San Franciscans find affordable housing opportunities by providing housing at lower than market rate units. So right now I have this layer. I want to understand what this layer contains, so I can right click on this layer and open data engineering. So data engineering, like as we kind of on a higher level know, it's just like this step of preparing your data before doing any analysis, just understanding it, visualizing it, and maybe cleaning it up a little bit before performing any analysis. So that view, this name comes from that, because in this view, what we can see, we can start visualizing some of the fields that this data set contains. So I have all these fields, some of them are text, some of them are date, numeric, And I can get into more details about each of these fields if I click calculate, and I get all the summary statistics for each of the fields. So this is like your comprehensive view of your data. You get things like, in this field, what's the minimum value? What's the maximum value, mean, standard deviation, all the way up to some sophisticated statistics like skewness and kurtosis to help you understand the distribution of your data better. So since this project is all about finding affordable housing, one of the fields of my interest is this affordable unit, like percentage of affordable units. So right off the bat, using the chart preview, I can see that this looks like a bimodal distribution. So either the fields are extremely at right or at left. So I can open a histogram to understand this field a little better. And clearly there are two different types of projects in my data set, right? Like one with almost all the houses at affordable rates, and one type of projects have just a few affordable housing available. So I do want to persist this information because using the histogram, I can see it, understand these two different types of projects that I have. But to really use it in any analysis, I want to persist that information into a categorical field. So I want to categorize these projects into these two different categories that I'm seeing right now in the chart. So if I right click, there are a ton of tools that are curated to clean, construct, integrate, and format your data. Just any data engineering process involves some of these steps. So in this example, I want to reclassify this field, convert it to a different format so I can use it in my analysis later. And once the tool opens, I can say that I want to manually classify these two categories. So what I would say is, like, if a project has less than 50% of the houses available at affordable rates, those projects are mostly at market rate. And similarly, if a project has more than 50% of the houses at affordable rates, so that project can be categorized as mostly affordable. And I can run this tool. When that happens, a new field gets added in my data set that would have these two new categories. So let me show you, the new fields get added here. And I can also see the statistics for these new fields. So right here, this is the new field that got added. And now I can see that there's almost a 60-40 split between 60% of my projects are mostly at market rates, 40% of my projects are mostly at affordable rates. That really helps me understand my data set better. And also now I can use this in any analysis. Another field of my interest, like for this example, I want to look at what projects are under which supervisors in my data set. So if I update the symbology of my map for this field supervisor districts, I can see there are about 11 supervisors. And then I can also quantify, let me show you, like I can create this chart to see how many project units are under which supervisor. So right here, this supervisor is taking a lot of work. Like this is the entire downtown area, and there are so many project units that are under the supervisor. So now what I want to do is I want to balance this workload. I want to make sure that all these supervisors get almost equal number of projects to supervise. And then for that purpose, I'm going to use the build balance zones tool that we just talked about. And to get us started, I want to use my input feature as this affordable data layer. And then here, I want to define specific number of zones. So since I have 11 supervisors, what I really want to do is create 11 zones. So each supervisor would get almost similar number of project units to handle. And once the tool completes, let me close a couple of things here. Okay, so now the tool has created these several different zones. And just by looking at the result on the map, we can see that that big cluster of downtown areas split into different zones. And to really see how that looks like on a chart, now we can see that those 11 supervisors have almost equal number of project units to deal with. There are so many different things that you can do, so many different things that you can balance in your data set. One of them is like you can also balance compactness. So what you want to do is you want your zones to be more compact. So in this example, I don't want one supervisor to travel a long distance to manage all the different projects that they're looking at. So I want those zones to be more compact. You can also balance distances. So if you have a headquarter, you do want to balance those distances again, that your supervisor doesn't have to go larger distances to supervise their projects. You can also balance categories. So if you remember, we saw that there's like a 60-40 split between affordable houses and market rate units. So what I want to do, I want to balance that information. Let me just like drag and drop this field. I want to balance this field so that each supervisor gets almost this 60-40 split in the assignment of their work. So we want each supervisor to have about 60% of units that are at market rate and 40% that are at affordable rates to kind of maintain that or mimic that overall data proportion. And once the tool completes, let me show you here. So now we have 2 things, or maybe 3 things. I would say like there are 4 things the tool has actually optimized, not 3, because one is spatial, which is hidden, you wouldn't know, but one is it's also creating 11 zone. It is balancing the compactness, it is balancing the proportion, and one that's hidden is the spatial constraint, that these zones need to be spatial. So there are 4 constraints that tool was trying to balance. So let me look at the quality of the results. So here I see there are 11 zones, and each of the supervisor is getting more projects that are at market rate than the affordable rate. That's exactly what we wanted to balance. And we can also look at the number of projects that the supervisor will be looking at. So here we see that we have lost a little bit of accuracy as compared to the earlier tool run where we had only like 1 constraint, but here this is the trade-off between if you add more and more constraints, it's a spatial optimization problem, so it gets harder and harder to solve. But there are some attributes in the tool like advanced parameters that you can tweak to probably improve your results. So if you increase the population size or number of generation, that increases your search space. So that increases more combinations of these zones so that the tool can find a different optimized solution. This is one of the optimized solution, but then you can tweak it to find a different optimized solution based on the results that you're seeing.